Okay, well, thank you for the opportunity to talk today. It's always interesting to see how the conversation begins to evolve throughout the different speakers. Important for me, coming from a studio that serves as a consultancy and a design studio within a large firm, we're consistently thinking about reconciling the question of what to build with how to build it. And I think what becomes apparent as you think through this is that if we can start to infuse or influence what we build with a better understanding of how we're doing that, we're going to have a better outcome. But thinking about that gap that has existed, between the what and the how, I'm not really so much interested in narrowing that gap because I think the gap itself offers a very useful space for exploration. And the way we kind of look at it is if during that exploration we can find a question that leads us to something else, we can kind of redefine what we consider to be useful. So with that in mind, I want to kind of frame the discussion today over where we've been, where we are, and where we're going. And useful to that is thinking about some of the stadia that we've done in recent years. And so about 4 years ago, about the time Line was beginning, we began to look at the Minnesota Stadium in partnership with TT. A lot of computational design going on from the beginning with the conceptual design stage. We worked really early in the competition, and then Line as a studio kind of pulled away and then re-engaged later in the process to start to think a little more heavily about how we got this from the idea of what to how we do it. But essentially with this project, we were thinking about things that included materiality, kind of redefining the experience of someone in a stadium. And with this project, we had the idea of clear as the new operable. So there was an ask by the client and many of the owners at this time for an operable roof. And with the climate of Minnesota, we presented the notion that perhaps instead of an operable roof, we could essentially give them something that felt like an open air stadium with the benefit of retaining some of the heat. So we started to explore how could we create a large expanse of ETFE on the roof that would allow us to give this kind of daylight but still be inside. And there were many interesting things that we were thinking about in terms of environmental sustainability and how we kind of reprogrammed the way we would use a multi-purpose stadium. But the interesting thing, and I think the thing that really presented the question that led to evolution of our workflow was some simple facade rationalization and the idea of taking some subtly warped compound curvature in the facade and manipulating that in a way that we could mate up with the structure behind it and allow the very thin zinc panels to be applied in a way that was that fit the aesthetic that we were going for. So with that, we're going to talk a bit today about where we are now. And we've been working on the LA Rams Stadium, which was officially broken ground about 2 weeks ago in LA, just east of LAX in Inglewood. And we've kind of tooled our workflow and changed our computational workflow a bit based in part on what we've learned in the previous projects. And so just introducing this one, we have an aluminum skin that's enclosing about 2 acres of open plaza, 6,000 seat performing arts venue, and a world-class football stadium. It's about 300 acres total land redevelopment. The stadium is just a small part of that. A couple of images to kind of situate ourselves here. You can see we have a very organic kind of flowing enclosure that serves as a roof, but it's an open air stadium. Located in Southern California, we did some pretty extensive climate analysis using a lot of tools from people that we saw earlier today, and we thank you for that, to determine ways that we could kind of enhance the natural ventilation, the airflow through the stadium so that we wouldn't have to enclose it and really pump up the HVAC. So to kind of see where we're located here, we're right straddling the line between 2 climate zones, and we were able to kind of really establish a strategy that allowed us to use a perforated aluminum skin in concert with some clear ETFE operable panels to really enhance airflow and kind of provide a really nice environment year-round for someone in this stadium. So, I'm going to introduce the problem, and then we're going to kind of talk through what we've done to kind of solve this. And I want to stress that this represents kind of a snapshot in time. This is where we are right now. And as you know, the criteria that we're working with, the constraints, budget, schedule, these things are constantly in flux, and we're trying to work through this in a way that we can respond to those. But essentially, how do you design, develop, document, and fabricate a system comprised of over 75,000 uniquely sized and perforated panels? So, saying this, first question that comes to my mind is why would you want to do this, right? Why not have a modular system? Well, essentially, that goes back to the question of what to build and how to build it. And the team kind of developed this idea, and it really started to fit and work with many of the criteria that we were working for. And we like to use a project as a way to develop design-specific, project-specific intelligence. And here, rather than question whether we should do these panels uniquely, we actually, started to work with the fabricator early on and started to understand the tools, the process, and the constraints in a way that we could exploit those and kind of tease out, can we do this? And with that, talk through some of our constraints. Many of these dependent upon time as well as cost. We have 8 hole sizes for perforation. We want to keep it under 52 million holes that we're punching. And we need to keep larger than a half-inch spacing between the holes for the web of the aluminum based on the thickness that we're using for the panels. The detail for the perforations is essentially just a coin to die punch. And the panel constraints themselves, what we're working with that we're going to show today, we're trying to keep them under a 4-foot width and within 10 degrees plus or minus of an equilateral triangle. And so that's a way to allow us to arrange these in a way that we can maintain a consistent material grain over the rolling shoulder of the roof. And so as we lay this out, you can kind of see the stadium portion itself in the elliptical area there. And we start with kind of a series of radiating grid guidelines. And those start to kind of fall off and follow the profile as we go around. From there, we start to lay in the joist framing, the main structure, and then we get the structural framing that starts to make up the depth of the system.
So we've all seen this kind of system employed before, where there's a base image. The base image is kind of what defines the texture for the perforations on this particular skin. Early on, there was a half-toning image that was used for visualization, and the designers were married to that. But that didn't provide us with a level of local nuanced gradation in the hole sizing on a per-panel basis. And we're going to just briefly describe kind of what we employed to do that. So rather than develop an entirely new image that would be mapped on to achieve that local density or local variation, we sort of superimposed 2 versions of the same image. And ultimately, that would allow us to kind of dither or create a kind of subtle gradation locally while creating this kind of halftone presence from the distance. One thing that we actually left out is that when in our conversations with the fabricators, it was revealed to us that they'd be using a coin die punch CNC machine. This particular machine has 8 opportunities, and that's why the 8 hole sizes. It has basically 8 positions that allow for the different hole sizes to be fit to that machine, and then the sheet would be cut. The sheet would be moved on the table, and the punch would be fixed. But with having the unique triangles, and rather than having all equilateral triangles, rather than employ a standardized perf grid, we developed a system to subdivide that grid on a panel-by-panel basis. So the constraints are the minimum edge length of every panel is determined, and then that minimum edge length determines the number of divisions, and then the perforation grid is plotted relative to that panel. So if you look at the 2 cases on the left, you see 2 sort of standardized grid, orthographic or square rectangular grid patterns, and then you see the residual spaces that are left at the edges with those 2 types of system. If you have acute triangles that sway outside of equilateral. So the other area that we were looking at was then how do we create that kind of local gradation and control the amount of total holes within the system. So and this was kind of treated as a sort of threshold. So if we were mapping grayscale values from the image, 0 to 255, where would we want the threshold for white to be, essentially where there's no hole. So on the far left-hand side, it would be treated as every grid position that's on the panel receives a hole, and the smallest hole represents white. Versus on the far right-hand side, we set white at somewhere around 125, I believe. And so you get a lot more pooling. It sort of translates into contrast, but it's not manipulating the image to achieve that contrast. It's manipulating how the perforation is mapped to the value that it's receiving from the image. And this is just a series of studies that were related to the tiling and how we would be able to sort of negotiate that local gradation against like the perception of the texture of the distance. And then some more of those. So the process, as I had said before, we worked directly with the fabricator. In this case was Zahner. And we ascertained from their input that one of the bottlenecks that's typical of this kind of process is the description of the geometry. If it's a representational or model-based geometry, there's a series of translation steps that have to go or have to be performed before they can automate the fabrication. So what we adopted was an approach that rather than build the geometry for each panel, we would actually just describe that geometry in terms of its text or geometric coordinates. And so we developed a sort of nomenclature and a tokenization, initially using Rhino and Grasshopper to tessellate the surface, but then extracting only the pertinent data from the world coordinates of each one of those panels. We have the 3 vertex positions in world space for the node, and then, which is the actual center point between seams. We have the corresponding UV parameter in each one of those node values, and then we have the normal and panel name for that particular panel. So we basically distill that piece of geometry down to somewhere, I think, like 8 to 9 lines of instruction. The next step within that, so we actually have multiple. We have a visualization process, but we also have the fabrication process. Before we can send out the files for fabrication, we need to somehow assess what those panels look like. So rather than, since we're not actually building a model of the geometry, how would we do that? In this particular case, we decided that it would be best to build an alpha map for each particular panel, and then that alpha map would be then mapped back to the parent geometry, so that we can basically render out each panel as a with its transparency without actually punching the holes into the geometry and creating a very dense mesh for what is essentially a triangle. That then in turn led to the process of mapping all those materials onto the geometry in Max, which was a very elegant 10 lines of code to basically draw the JPEG or a texture map file, map it to its own material definition, and then correspond that to the tagged piece of geometry in the Max file. Again, all just to visualize. This was actually one of the more computationally intensive parts of the process, just in terms of producing the abundance of JPEGs. But then going back to the production of the text files, like I said, we also developed a way of producing drawings, but as I said, in this particular process, it's kind of, it's superfluous. You don't really need the drawings, and if nothing else, it was just to prove the concept that we could. Ultimately, we want to omit this part of the process altogether. So what exactly do those text files contain after going through the process of mapping them into a 2D coordinate space? So each vertex is then mapped such that the first vertex becomes the origin in machine space, and the corresponding positions for all the subdivision points of the perforation grid, and the size of the perforation or tool number for that particular perforation. There's some additional data that's provided in the text file that describes that. Everything from the area, the opacity of that particular panel, all of this stuff was simply to allow us to get to a point where we can run analytics on the total system.
The analytics are very, very telling, and I think kind of explain the necessity of what we're doing to keep up with the timeline. I know we're just about out of time, so we're going to hit this real quick. Where we're going, I think, is more about kind of getting some questions. So if you want to run through this, and we'll show some images, maybe generate some conversation.
So sort of to validate the process, because we could have done this using Grasshopper, and if you look at the bar graph, the white lines represent what the computational time was per batch of panel to produce that same set of documents using Grasshopper. And actually we didn't do the entire process, we just isolated the most computationally intensive part of the process, And then the red bars represent our framework that we developed in C++, both as a single-threaded and multi-threaded version. We tapped out somewhere around 10,000 panels for the calculations. We're running at around 20 minutes in Grasshopper, so I stopped conducting those trials and then picked those up only using single-threaded and multi-threaded versions. And as you can see, there's sort of a diminishing return as the batch sizes increase, but on the far right, we've got 27,500 panels, and about half the time to calculate that using a multi-threaded option. So where is this all going? One of the things that I think we think there's an opportunity for, and maybe is there's some questioning that needs to be done in how we describe geometry for fabrication, and whether or not we should be employing a model-based approach on all applications. Obviously, in this case, it's a simplified geometry. For the previous case, it's a simplified geometry. But it is apparent that there are performance gains in going direct to a process description or a discrete geometric description that can then in turn be post-processed into a process description. So the images that Heath's thumbing through now is some of the work that we're, basically the framework that we employed this on was being developed for some work that I'm doing in my PhD, which is related to robotic fabrication and additive manufacturing. So the idea is that if you're going to describe a piece of geometry in its most discrete form, can you then jump directly to a machine protocol rather than describing it purely in terms of geometric representation, then post-processing that geometric definition into something that describes paths or bending operations or what have you. And so these are just some slides from that PhD work, some of the part definitions. Ultimately, what we're hoping to do is not only describe the panels, but move into a case where we would describe the actual node connector, which is also as complex in terms of its variability and differentiation within the system. How can you structurally optimize that per location and describe it in terms of something that's a little bit more discrete, ultimately going direct to fabrication. Obviously, that's looking forward. It's not something that we're on top of at this point, but it's where we're seeing some of this work go.
And essentially teasing out the question, we asked, can we 3D print the nodes in the stadium? A few people laughed, a few people walked out of the room, a couple people said, let's look at that. We lack the fabrication capacity now. With the next stadium, we may have some 3D printed material.
If I like capacity, I think it's important to say we as an industry, not just we as the firm. One of the things that we've discussed with the industry that's at the forefront with the largest capacity for metal 3D printing is that this particular node could be printed, but there's only a handful of those machines that are operated by OEMs. They're not for-service machines. And if you were to run the entire batch of for the entire system, we'd be looking at close to 3 years of running time, assuming you had 15 machines available in 24 hours a day for the next 3 years, and no failures.
2019 opening, so we should be good. Thank you.
Cost consideration.